Okay, so this is our presentation about Hilltop Runoff, and it is by Zach Streza and me, David Zulo.
Hello, I'm Zach.
Okay, so what is the problem that we're trying to solve? It's all about runoff. So our campus has a lot of impermeable surfaces, like concrete and asphalt. And basically, what impermeable surfaces are is just water that doesn't get absorbed into the ground. So it can't get through that surface. So it gets trapped at the top. So if the water gets trapped at the top, it has to go somewhere. So it either goes into the sewer or it runs down our hillside into the valley on each side, and that can be a problem because they can flood, and it carry the water as it goes down the hillside and the roads. It actually picks up salts and other pollutants, so that can be very bad to put into our water. So we want to try and fix this and help mitigate the amount of water that gets run off, and we want to try and get it to seep into the ground.
All right, so how much water is there running off of these impermeable surface David was talking about? So what we did was we calculated the average rainfall over the past 5 years, 10 years, and 30 years. And we used this average rainfall to calculate what volume of water is actually running off these impermeable surfaces. So what is this water that's staying up? So we found that for the average rainfall of the past 5 years, we found 73,835 cubic meters of water that get did not soak into the ground. That just ran off our hilltops, stayed on the hilltop, and just evaporated back into the air. So this does not help replenish our groundwater sources at all. Um, and with the past average rainfall for the past 10 years, we saw 68,861.75 cubic meters of water. And in the average rainfall of the past 30 years, we saw 61,848 cubic meters. Now, with the average rainfall of the past 5 years, we saw that was a little high from the past, look at the average from the past 10 years and the past 30. So we want to make sure that was consistent with rainfall over the past 50 years. So we made a little graph here just to make sure this is all the average rainfall, or I shouldn't say average, this is average rainfall. This is the amount of, this is the total precipitation we had over the past 50 years. So you can see that we are at a high point right now at the very end of this graph. So we're at a little high point, but it is still rather consistent with everything else in the graph. So we are okay. Everything's consistent.
Okay, so how to find the elevation? So we use contour maps, which, as you can see in this picture, it has different numbers. So those numbers are going to tell us the feet from sea level. And on the next slide here, you'll see the maps that we use. So these are the maps of our campus, the contour maps. So we were able to look at these to find out the exact elevations of everything and the steepness of all the slopes to see how much gets run off and stuff. Okay, so our original idea was the abandoned basketball court next to our high school. So using the contour maps, we were able to see that this was at a lower point than the high school. So this road, the roads right here, actually the water is going to run down those into the basketball courts. So we wanted to try and find a way to mitigate the water from just sitting on top of that basketball court and collecting. So we wanted to add some either greenery or something called a rain garden there.
So since David mentioned a rain garden, this is what a rain garden is. So this was our original idea. And a rain garden is just your typical average garden, but they're just a little special because they're designed to hold water temporarily to allow this water to soak into the ground. So and when you hear rain garden, you're probably thinking you're thinking kind of like a swamp or kind of marshy because you're thinking it's always going to be wet. That's actually very wrong. Rain gardens are almost always dry until a rainstorm happens, and they also drain relatively quickly within 12 to 48 hours. So most of the time, these guys are dry, not like a marsh. So and you kind of form these from a little hole or ditch on a natural slope. In this case, we already have an area of flattened land in the old abandoned basketball court, and since it is on a natural slope, we placed a rain garden there. The water would just collect there. And so your typical rain garden will consist of native shrubs, native flowers, and native perennials, because we don't want to put anything non-native there that could be potentially invasive and harm our wildlife even further than the amount of runoff. So what would the rain garden cost? Well, this is where we ran into a problem because the area of our old basketball court was 50,458 square feet. And if you don't know, like just in comparison, that's a very, very large area, much larger than we originally expected. So since a rain gardens have to be dug out like 6 inches into the ground. So we had to figure out what the volume of that would be. So that would be 7,729 cubic feet. And you're probably wondering why that like the volume is much larger than the area. Well, that's just because 6 inches equals half a foot. So still the same thing, but just a little bit different. So in the end, our estimated totals though, we the cost for our ring garden though for the size of it would have been $70,622.83 to $138,000 $205.83. Now that's a large amount of money, especially for a middle income area like the North Hills. We would probably never be able to go through with a ring garden of this size. And it's not even saying that the ring garden would work. It's just a plan that could work.
So our problems with the original solution. So like Zach said, it proved to be way too costly. And upon walking around the campus, we found out that they actually have storage crates that are on the basketball court. So they probably wouldn't want us to take those out. So we had to come up with a new solution, and that was to add green spaces to the parking lots. This would be a much smaller and more doable surface area, and it would be much cheaper, and every little bit helps. So if we add green spaces here and there, that's way better than just having all concrete and asphalt. So we saw that in some of our parking lots, we already had green spaces like this. These are pictures of our parking lots. So if we go to the next slide, we'll see these are the types of areas that we want to add them to. This is another parking lot on our hilltop. These are just asphalt with painted lines in them. So if we have green spaces already, why can't we just add a couple more? Because every little bit of green helps.
So as David was saying about the green space, we wanted to figure out how effective this would be and how much water this would actually absorb if this was 100% effective. Chances are it's not going to be 100% effective. Some of the water could still run off of the area, but if it was, and all the water that landed on that plot of land just soaked into the ground, we found that it would probably, for using the rainfall for like the average rainfall over the past 5 years, we would find it would absorb 619.78 cubic meters with the area we want to turn into green space. Now, we probably don't know what a cubic meter is, like off the top of our head. We do know what a gallon is. So we converted this, the cubic meters into gallons, so it would be a better picture to understand. And basically that plot of land, like the little plots of land you were just thinking about turning to green space, that would save 168,728 gallons of water from running off our hilltop or just evaporating and staying there in puddles. That's just not going into the ground. And with the average rainfall the past 10 years, we would see 182,000 gallons of water. And with the average rainfall the past 30 years, we would find 137,000 gallons of water, all absorbed by this little bits of green space. So in the conclusion, every little bit helps. So it's not going to be one giant solution that can solve runoff, because especially with a larger campus, and especially since we're on a hill, hills are surrounded by all sides. So you're going to have it where we're the highest elevation. So you have to figure out how to stop our runoff on every single side of our hill. So one little rain garden on one side of the hill won't help the other side of the hill. So we have to just try to capture as much of the water we possibly can. And the harsh reality of it is we can't capture all that water. When you take away those like forests and you take away those permeable surfaces and replace them with asphalt and concrete, that water will never go back into the soil, and there won't be as little water running off as there would if it was a forest. That's just the harsh reality of it all. And even if we want to do that, cost is a big factor. If we wanted to make our hilltop 100% permeable, it would cost a lot of money. And as I mentioned before, it's the middle income area. We're not going to be able to have that money. because when it comes to our district, our students come first before our campus and the amount of runoff going off of it. So in the end, as I mentioned, our solution is just low cost plans to allow water to seep into the ground, because anything, as I said, like every little bit helps. So, and that is the end of our presentation.
Yep. Thank you
Thank you
for
for you
watching.
guys listening. We appreciate it. Anything you want to add, David?
Nope, it sounds good.
All right. See you guys.